In this video, we're going to learn how to calculate the cell potential. The cell potential being the voltage that a galvanic cell can provide for us to drive an electrical device. All right, so just to remind you, cell potential is going to be indicated with an epsilon, and it's basically talking about the voltage that that galvanic cell can provide us. It is also known as the electromotive force because it's basically the driving force that drives those electrons to go from one cell to the other cell. A volt is defined as 1 joule of work per coulomb of charge that is transferred. Coulomb is the unit that we use for charges that are moving. And so our volts is going to be equal to a joule per coulomb. And the way that that voltage is measured or that potential is measured is typically utilizing a voltmeter or a potentiometer. All right, so chemists have chosen to measure all of the cell potentials relative to the potential of the standard hydrogen electrode or SHE. The standard hydrogen electrode is shown here and is basically showing the reduction of hydrogen under standard conditions. Standard conditions means that the hydrogen ion concentration is at 1 molar and that the hydrogen gas, which is actually on the electrode itself, is at 1 atmosphere. Notice that this is a weird electrode in that we still have platinum electrode, but we're introducing hydrogen as a gas. And this is one of the cells. The other cell would be a normal reaction, like another chemical reaction happening. And that's the one that we're trying to measure relative to this one. Now, the standard hydrogen electrode has been set to be a voltage of 0. And so all of the other ones are going to be measured relative to this one. All right, standard conditions, just to remind you, is that if we have a solid or a liquid, they will be pure substances. Any solute will be dissolved at a concentration of 1 molar. Any gas will be at a pressure of 1 atmosphere, and the temperature will need to be at 25 degrees Celsius, which is the same thing as 298 Kelvin. Now, what it says here is that we're going to have tables that have the values of the cell potential. And I should say, so we're going to have tables that have the values of the cell potentials for specific chemical reactions. If we pair 2 of them together, we can actually calculate the cell potential by utilizing an equation between those 2. And I'll show you the equation in just a little bit. All right, so these are the tables. In your book, the table is number 19.2, and there's also an appendix A5 that contains more of them. But of course, Sapling will also have a link to their table. In this table, what we have is that we have a number of chemical reactions. Notice that in all of them, we have electrons on the left-hand side of the equation, meaning that all of these are reduction equations. So here, for example, fluorine is being oxidized by addition of electrons, it's being reduced by the addition of the electrons to form fluoride. At the very bottom, we have the same thing. The lithium ions are being reduced by addition of electrons to form lithium solid. Now, on the left-hand side, we have the reduction potential associated with that reduction process. At the very top, we have the most positive. At the very bottom, we have the most negative, and they are in order. Now, being at the very top means that this reduction reaction, is highly likely to happen. So the fluorine is very likely to be reduced to form fluoride ions. On the other hand, having a very negative reduction potential, it means that the reaction as written is not very favorable. Instead, what is likely to happen is that lithium will oxidize to form lithium ions and release electrons. So the opposite process is more likely to happen. Okay? So in the previous slide, I told you that if you had a table like this, you could actually select 2 of these reactions and figure out what the cell potential would be for a galvanic cell in which you use 2 of those equations. But remember that one of them has to be a reduction, the other one has to be an oxidation. Whichever one is higher up, whichever one has the higher reduction potential, that one will be your reduction. Whichever one is lower and has a more negative reduction potential will actually be the oxidation. So the oxidation, remember that you have to flip the equation to show an oxidation process where you lose electrons. And when you flip the equation, the reduction potential would change to be positive, would change to whatever the opposite sign is, and it would not be called reduction potential anymore. It would be called the oxidation potential, right? So we can select any two of these equations. The one that has the more positive reduction potential will be the reduction, and this will be its reduction potential. And whichever one is lower will be the oxidation, and the reaction will be flipped and its sign will be changed. And that's what it says here. From the same table, this is indicating the same table that we had at the top. Remember that the fluorine was at the very top. We said that that one was the easiest one to reduce. It is therefore the strongest oxidizing agent. On the other hand, on the bottom, we had the reaction for lithium. But the product, the lithium, is going to be the easiest one to oxidize and is therefore the strongest reducing agent. All right, so now I have a question for you guys. Which of the following halogens is the best oxidizing agent? We have fluorine, chlorine, bromine, and iodine. They're all written as a reduction in that we have the electrons being added, and you're providing with the potential for each of those reductions. So this is the reduction potential for each of these. They're asking us which one is the best oxidizing agent, and I'll let you guys think about it for a second. All right, so in this particular case, the best oxidizing agent is going to be the one that gets reduced. And the one that gets reduced is going to be the one that has the most positive reduction potential. In this case, fluorine is going to be the one. It has the most positive reduction potential out of all of those, so it is going to be the best oxidizing agent. All right, so in order to calculate the cell potential, I told you that you could pick two of those equations in the table. The one that is the most positive is going to be your reduction, and that reduction occurs at the cathode, and you can just write down the number directly from the table. Now to that, you're going to add the oxidation potential. But remember that the table only has reduction potentials. So whichever one is our oxidation, we're going to flip the equation and we're going to change the sign of the reduction potential to become an oxidation potential. And that's what I say here, basically. To figure out your oxidation potential, you're going to put a negative sign on whatever the original reduction potential was, and that makes it into an oxidation reaction. Of course, the oxidation occurs at the anode, and ox and red cat, right? And just to remind you, in this equation, we have that little zero symbol. That little symbol indicates standard conditions, which is that if you have a gas, it is going to be at 1 atmosphere. The temperature will have to be at 25 degrees Celsius, and the concentration of all your solutes will need to be at 1 molar. All right, so how do we predict the reduction in the oxidation in the galvanic cell? Well, I already told you that the most positive reduction potential will be your reduction. The other one becomes the oxidation. The reason for that is that your cell potential needs to show a spontaneous reaction. A spontaneous reaction will produce a positive cell potential. And for you to have a positive cell potential, the reduction needs to have the more positive cell potential, and the oxidation needs to have the other one, basically. So your cell potential will be positive. If the cell potential was not positive, then it would not be a galvanic or voltaic cell. It would not provide you with electricity. Okay? Similarly, positive potentials for cell potentials are associated with spontaneous reactions. Okay, so your cell potential is positive. That indicates that you have a spontaneous process. And you know that a galvanic cell utilizes a spontaneous reaction, which means that the cell potential needs to be positive. If you had a negative cell potential, That would not give you electricity again. That would not be a galvanic cell. Instead, it might be an electrolytic cell that you are driving by applying a voltage to it. And I'll just leave it at that. All right. Sorry, so we have the example. Consider a galvanic cell that is based on that reaction provided. And the half reactions are given there with their respective potentials. Notice that here we are given two equations where the electrons are on the left-hand side for both, which means that both of these are reduction equations. If you look at the top, that's not exactly how they are written. So sure, the aluminum 3 plus is on the left-hand side and the aluminum solid is on the right-hand side. But the magnesium is not in the right way, right? The magnesium here is the solid, should be on the left, and the 2 plus should be on the right. But that's not the way that was given to us. So by looking at the equation, we already know that this one is supposed to be flipped. Now, I didn't actually have to give you this. I could just give you these two without showing you this equation. And you should have been able to figure out which one had to be flipped by looking at the cell potentials. The more positive one, which is this one, will be our reduction. So I'm going to go ahead and label this top one as reduction. Even though it's negative, it's still more positive than this one. And so this one is going to stay as is. On the other hand, the other one is going to be our oxidation, but to be the oxidation, it has to flip, it has to be reversed, right? And when it reverses, the sign of this is going to change. So the oxidation potential becomes positive 2.37 volts. And now this is going to be our oxidation. Of course, I need to rewrite this in the proper way. And let me see if I can do that here. I can write my magnesium solid goes to magnesium ion 2 plus 2 electrons. All right, so now my equation is written as an oxidation properly. The question in this problem was A, give the balanced cell reaction, okay, and then B, calculate the cell potential for the galvanic cell. Perfect. So for A, what we're going to do is that we're going to take our reduction equation and our oxidation equation, as I have written it down here, and we're going to add them together. So to add them together, I need to have the same number of electrons in both. So I'm going to just go ahead and write those two equations down here independently. My reduction was the following. Aluminum 3 plus 3 electrons goes to aluminum. And my oxidation is that I have magnesium going into magnesium 2 plus 2 electrons. All right, to be able to add these two equations, I need the same number of electrons, which means that I'm going to be multiplying the top equation by 2 and the bottom equation by 3 to get to the smallest common multiple, which is 6. And then I can rewrite my equations with the new numbers and then add them together. So the first one becomes 2Al3 plus 6 electrons goes to 2 aluminums. And then the other one becomes 3 magnesiums goes to 3 magnesium ions plus 6 electrons. And now I can add them together. So of course my electrons are going to cancel because that's what I did by multiplying the two by coefficients. And now I can add them together and nothing else cancels away because all I have is aluminums and magnesiums. So I can just rewrite the whole thing as 2 aluminum 3 plus 3 Mgs goes to 2 aluminums solid plus 3 magnesium ions. And we are done. We are done with part A, which is to give the balanced cell reaction. Part B is to calculate the cell potential for the galvanic cell. And we can actually do that up here. So remember that the cell potential for the galvanic cell is simply the sum of these two values, the sum of the reduction potential plus the oxidation potential. So E0 of my cell, and the 0 indicates just standard conditions, is equal to the potential for the reduction at standard conditions plus the potential for the oxidation, which means that I'm going to take my reduction, which is negative 1.66, and to that I'm going to add my oxidation potential, which is 2.37 volts, and that gives me a total of, let's see, what was it? 0.71. And we are done. That is the answer for the cell potential of our voltaic cells. And of course, we want to make sure that this ends up being a positive value, otherwise it is not a galvanic cell. Otherwise, we have made a mistake for this galvanic cell. All right. Next example, we have a voltaic cell is based on the reaction shown there. The two half reactions are provided. And again, notice that both of them are written in the reduction form. And we are asked to give the balanced cell reaction as well as calculate the cell potential for that particular galvanic cell. All right. So what we're going to begin with is by, I guess, doing the first part, which is to do the balanced equation. So first thing that we want to see is which one of them needs to flip, which one of them is written in the incorrect way. We can do the two different ways. One by looking at the equation given up here. The second one is by looking at the cell potentials. Whichever one has the highest, most positive cell potential, that one is going to be the reduction, and so it's going to be left as is, as a reduction with the electrons being on the left-hand side. The other one, which is this one in this case, is going to have to be reversed to become an oxidation. So let me go ahead and write that this one, oops, is my reduction, this one is my oxidation, but of course to be an oxidation, it needs to be rewritten as ClO3 minus plus water going into ClO4 minus plus 2 hydrogen ions, oops, plus 2 electrons. All right. And of course, when you flip the equation, the sign of this changes. It was positive, it now has become negative. Ooh, I'm not going to see that, am I? Negative 1.19. And this is my oxidation, this is my reduction. Oops. All right. So to balance the equation, I now have to take this equation and this equation, and I need to make sure that I have the same number of electrons. This one has 5, this one has 2. To get to the smallest whole number that is common among those two, I'm going to have to multiply this equation times times 2. Oops, I do not mean to highlight things here. Sorry about that. I need to change this. Okay, I need to multiply this times 2. And I need to multiply the next one by 5 to get to 10 electrons, which is the smallest multiple. So I'm going to write this here at the bottom. I'm going to have 2 MnO4 minus plus 10 electrons plus 2 times 8 is 16 H pluses goes to 2 Mn2 plus 8 waters. Oops. Come on, right. All right. For the bottom one, I'm going to have 5 ClO3 minus plus, notice that I'm actually multiplying this one, right? The one that has already been written as an oxidation. So I really should have said that this is the one that I'm multiplying by 5. So ClO3 minus plus 5 waters goes to 5, oops, goes to 5 ClO4 minus plus 10 H pluses plus 10 electrons. I am going to add those two equations up together. So I start by canceling away things that can be canceled, which is the electrons to begin with. I made them 10 electrons so they could cancel. And then I begin bringing things down. So my permanganate ion can just come down because it cannot be canceled with anything else to MnO4 minus. I've taken care of that one, so I'll go ahead and indicate so. Let me see, is there anything else? Actually, I can deal with the hydrogens now. I have 16 hydrogen ions on the left-hand side, and on the right-hand side I have 10. 16 minus 10 is 6, so I can go ahead and say that I have 6 H pluses left here on the left-hand side. Let's go ahead and mark those hydrogen ions away. The next thing that I'm going to deal with is waters. I actually have 5 here on the left, and I have 8 on the right, which means that I'm going to end up with 3 on the, let's go ahead and put an arrow here, 3 waters on the right hand side, because there were more waters on the right than on the left. And I can go ahead and mark my waters away. And now everything else that I have is going to come down. So my 5 ClO3 minuses come down. That's taken care of. And then on the right hand side, I have my manganese ions, 2 Mn2 plus, and my 5 perchlorates. Done. You might want to check always to make sure that you have the same number of atoms and charges on both sides, but it should be good. So that was the first part, the balanced chemical equation. The next thing is to calculate the cell potential. The cell potential is simply the addition of these two numbers now. So my E0 for the cell, cell is going to be equal to the reduction potential, which is 1.51 volts, plus the oxidation potential, which is negative 1.19 volts. And that gives me a total of, let's see if I can find it, yes, 0.32 volts. Done. That is it. That is my answer. All right, and again, notice that in this particular case, we didn't actually need this equation, so I don't need to give you that in the questions for the exams. I can just give you these two, and you can tell me in which way do they actually come together to give me a galvanic cell with a positive cell potential. Now, there's a possible chance that you're going to see a question where I do give you this equation. But when you look at how these equations match to that one, you're going to end up with a negative cell potential, in which case you can tell me that that is not a spontaneous reaction, and therefore I cannot use it to give me electricity, basically. It's not going to give me electricity. It's actually going to require electricity to occur. All right? All right, so let's continue on. Next example, calculate the cell potential for a galvanic cell that consists of the zinc ion half cell and a copper 2 plus half cell. And provide the notation, the line notation also for this voltaic cell. So again, this is a galvanic cell, which tells us that we need to have a positive cell potential. That means that we're going to be looking at these reduction potentials, and we're going to select the most positive one to be the reduction, which is going to be this guy. And the other one is going to be our oxidation. But to become an oxidation, since it is written as a reduction, we're going to go and change its sign. It's going to become positive 0.76, which means that the cell potential is going to be, let's see, the reduction, which is 0.34 volts, plus the oxidation potential, which is 0.76 volts, and that gives us a total of, let's see, 0.76, okay, that gives me a 0, and this is going to give me a 1.10 volts. Now the next part, provide the line notation for this voltaic cell. Okay, so in our line notation, we needed to have the anode on the left. The anode is where the oxidation takes place, right? And the oxidation is the opposite of this process, right? It's going to be the zinc 0 going into zinc 2 plus and 2 electrons. So I'm going to write it by taking my zinc, and remember that zinc in this form, that's a zinc solid, is the metal zinc metal. And then I'm going to have a phase change to my zinc ions. So, oops, why do you do little circles? Zinc ion, 2 plus. And I'm going to go ahead and put AQ for that one just to indicate that those are in solution. Then from there, we're going to have our change to the other half cell where we're going to have the reduction. The reduction for the right-hand side is going to be exactly as is written. So it's going to be our copper 2 plus going into a phase change into the copper solid. Oops. And that's it. This guy is AQ. This one is solid, and we are done with our line notation. That's that. I recommend that you guys go and look at this example and these practice problems to be able to practice a little bit more in terms of calculation of the cell potential and the writing, the way that they write the line notation as well. All right, now here what we're going to do is that we're going to be looking at how to provide the complete description of a galvanic cell. So that complete description is going to include the cell potential, the balanced cell reaction, the direction of the electron flow, which is going to be obtained by looking at the two half reactions and looking at where we have the oxidation take place, where we have the reduction takes place. We're going to design which one is the anode and which one is the cathode. We're going to look at the nature of each of the electrodes, like are we going to use an electrode that is part of the reaction, or are we going to use something else like a platinum electron. And we're also going to look at what are the ions that are in each compartment. So let's go ahead and do that. And we're going to draw a picture and show how everything actually comes together into a galvanic cell. So describe completely the galvanic cell using the following half reactions under standard conditions. Okay, so in this particular case, we are given two reductions, right? We need to figure out which one is staying as a reduction, which one is going to be the oxidation. Well, this guy is the more positive, so this one will be the reduction, and that equation will stay as is. And if you don't mind, I'm going to go ahead and highlight it, that one with this reduction potential. On the other hand, the other one is going to have to change to be an oxidation. I'm going to go ahead and rewrite it here as an oxidation. So Fe2 plus is going to go to, why are you doing that, computer? Let me write. Come on. It's going to go to Fe3 plus an electron. And the potential for that is going to be our oxidation, and that's going to be the opposite sign of whatever it was. So in this case, negative 0.77. Come on. All right. From there, we need to go ahead and get the balanced equation. The balanced equation is done by taking these two equations and making sure that they have the same number of electrons, which they do in this case, 1 and 1, and adding them together. And I'm not going to rewrite them, I'm just going to go ahead and write what's left. We know that the electrons are going to cancel away, but it looks like everything else stays. So our balanced equation is that Ag plus iron 2 plus is going to go into Ag as a solid plus iron 3 plus. Awesome. All right, now I actually have a diagram here that we're going to fill in the blanks and see what's actually in there. All right, so notice that I have my two highlighted equations. Those are the two things that are happening. This one right here where we are gaining electrons, that's a reduction. So that's going to be our anode, right? And in this particular case, I drew it such that my silver is on the right-hand side. So that's actually where I'm going to be putting my silver reduction. And I'm going to go ahead and write this side. This is going to be my reduction. The reduction occurs at the, let's see, at the cathode, right? So this side is my cathode. Awesome. And I'm going to go ahead and write that equation down here at the bottom where I have Ag plus an electron gives me Ag solid. Okay. Then that means that the other equation is happening on the left-hand side. The left-hand side is going to be my oxidation. The oxidation occurs at the anode, an ox and red cat. right? And notice that in this case, I have iron 2 plus and I have iron 3 plus. Those two are ions, which means that they are in solution, which means that I cannot use them as the electrode. So I need another electrode. In that case, I'm going to be using platinum. While on the other equation, I actually had silver solid, right? Silver as a non-charged element. And that means that I can use that one as the electrode itself. Awesome. What else do I need in here? I need to write my equation down here just to remind me what is happening in this process. Fe2 plus is going into Fe3 plus electrons. The next thing that I need to do is to show the electron flow. So notice that down here we have electrons as a product. Those electrons are going to come from there and they're going to go to the other side, right? Because they are the product of this reaction, but they are needed here as reactants. So the electrons continue in this direction to provide us the current. All right, the next thing that we need to think about is what is happening in this the bridge, in the bridge between the two cells. So remember that that bridge is going to have electrolytes or ions. And that could be potassium ions or sodium ions that are positive. And then for the negative, it could be nitrate ions or chloride ions. Let's say that in this case, if I told you that what I have is KCl. So potassium ions are positive, chloride ions are negative. I need to think about which direction are each of those ions going to go. On the left-hand side, I'm going from Fe2 plus to Fe3 plus. So over time, that solution is going to become more and more positive, which means that negative ions are going to have to come to balance that out. And the negative ions out of my potassium chloride are the chloride ions. On the right-hand side, over time, my silver plus is becoming silver solid. So I'm losing positive charges over time. That means that the positive ions, which is K plus in this case, are going to have to go toward that direction. So that is my salt bridge. The next thing that I want us to think about is what are the charges of the anode and the cathode. Notice that the electrons are leaving from this side and they're coming to the right-hand side. Electrons are attracted by positive sides, so my cathode is positive. Here, the electrons are going away from this place because it is a negative side, right? The last thing that I need us to think about is what's happening to the mass of the electrode over time. In this particular case, notice that the electrode, which is platinum, is none of this, right? So there's no change in the mass of this electrode. Let's go ahead and write that down. No mass change for electrode, because there's no formation or no use of the solid metal. On the right-hand side, on the other hand, I have silver ions that are becoming silver solid. That means that over time, my silver ions from the solution are depositing onto the electrode, and that electrode is gaining mass over time. So the cathode, which is the electrode, gains mass over time. I think doesn't want to write anymore. Gains mass. Yeah, you guys get it. I can barely write. All right. And it gains mass because silver ions are becoming solid silver. I recommend that you guys look at example 19.7 and practice problem 19.7 to get a little bit more practice on this topic.